The first speaker of this afternoon is Barney Bramham from Bochum. He will talk about an approach to some questions on Hamiltonian surface maps using pseudo-holomorphic curves.
Okay, thank you. And thank you for the organizers for inviting me. It's very nice to be here. Yeah, my talk is really motivated by a question of Michel Amann. Maybe maybe I shouldn't say an approach to it, because I have no idea, even close to step 0 in it. But it's at least something new and brings in a whole new set of tools, and it's sort of in the same neighborhood as this question, vaguely. And so that's what I'd like to talk about. And just because this is a conference on, it says, conservative dynamics and symplectic geometry, I thought I'd place this in in this symplectic geometry context of Gromov's, the notion of rigidity in symplectic geometry. I don't know if this is helpful, especially as I'm working in low dimensions, and then it's a bit difficult to distinguish what is rigidity and what is just because you're in low dimensions. But anyway, for what it's worth, that's what I'll with. So we've seen already this morning rigidity phenomena in symplectic geometry expressing itself in the sense of that the symplectic diffeomorphisms are closed in the C0 topology in diffeomorphisms. And of course there are many other ways in which this expresses itself, and I'm interested in this talk about dynamical expressions of this phenomena. And that's the context I'd like to place this in, to what I'm going to talk about. So what do I mean about this in a dynamical sense? So maybe I begin by illustrating with this, which I think is a very interesting fact, which is a Hamiltonian transformation is the identity map if and only if the actions of all the contractible periodic orbits are the same. So this is a somewhat imprecise statement. So it's basically saying that if you have what is a fairly small amount of information just about the periodic points, you're suddenly saying you know all about the whole dynamics. Okay, so here's a sort of one more precise version of this. So you could do this on closed symplectic manifolds with suitable assumptions here, say on R2n. We have, say, a time-dependent one-periodic Hamiltonian with compact support. And then this, to every periodic orbit, they're all contractible, of course, in R2n. We can associate this real number, the action of this, and the action function we all know has the critical points of this are the periodic orbit. So there's a close relation between the action and the dynamics of this of the associated Hamiltonian system. And so then the statement is that the actions of all these one periodic orbits are equal if and only if the Hamiltonian is identically 0. So of course the action is also then 0. And that is if and only if the time on map is the identity. And this, I don't know, makes one wonder. So this may not be helpful at all, but I'll still ask this. So to what extent are Hamiltonian transformations in general dynamics away from the periodic, the recurrent phenomena, determined by the periodic orbits? So this is very vague, and of course you're never going to know the whole dynamics in general from just the periodic points, and that's clearly ridiculous. But so what sort of information do I mean? Well, for example, the action, like we just theorem, and you could also say I want to know about the Conley indices of orbits, and if you're in low dimensions, which I will be then, say the linking numbers. And here then is a class of Hamiltonian systems where you know all about the periodic orbits. Shall I just hold this? Hello? Hello? Yes. Hello? Yeah. This is great. So here's some Hamiltonian systems where we know all about the periodic points, and But it turns out that the dynamics is, well, unsurprisingly, this is not enough to determine this. And but to what extent can you say something about the rest of the dynamical system? So here are the systems I'm talking about. So if there's one definition in this talk, I'd like you to try and roughly remember for the rest of the talk. This will be it. So this is talking about diffeomorphisms of just the standard closed unit disk, two-dimensional. And it's a very small class of them. These are transformations which are symplectic, they're area preserving and orientation preserving. And they have exactly one periodic point, which means that it has to be an interior fixed point. And by changing coordinates, you can assume that this unique fixed point is at the origin. So we're talking about systems that have a single fixed point at the origin of the disk and no other periodic points. Okay, so. And then this is called a pseudo-rotation. If you prefer closed manifolds, you could think of the two-sphere and just having two fixed points at the north and the south pole and no other periodic points. And an example of these are, of course, if you just took a rigid rotation on the disk about the origin that rotates by an irrational number. So obviously that fixes the origin, and then if you choose an irrational angle, there are no other periodic points, of course. So that's an example of them. So what else do we know about the dynamics besides that periodic point? We know everything now about the periodic points. You can work out what the Conley-Zehnder index is of this periodic point and the action and so forth. So do we know anything else? So first of all, area preservation forces the following property. This is, I think, actually due to John Franks. It tells you that if you take a point, so a non-periodic point, so not the origin, and you look at what happens as you go around, and then you look at the angle coordinates rather than the radial coordinates, then you can then talk about the average rotation number of this point, which may or may not exist, and it turns out that it always does. And so you add up these angles and take an average. And this limit will always be irrational. And it turns out it will always be the same for every orbit. And so this is just a property, a consequence of the area preservation. And that's not obvious at all. And so we have associated to this system a irrational number. And so we'll call this the rotation number of this pseudo-rotation. Okay. So a natural question at this point is it in fact even conjugate to a rotation globally, the whole system? So in other words, does there exist a change of coordinates with some kind of regularity? Even continuous would be interesting. That takes your system to rotations. In particular, the system on the left would then, of course, there would be all these invariant circles filling up the whole space that around the origin, of course. So let's just compare this with what would happen if this was true also on the boundary. So look at the one-dimensional analogous question. So, of course, this has an old history. So the question is, consider a diffeomorphism of the circle. And this has an associated rotation number defined in the same way we just said. And supposing this is irrational, and you ask, does there exist a change of coordinates that linearizes this, turns it into a rotation? If so, then the rotation has to be by the same angle that the rotation number is. That's clear. So, of course, this is a very old question, and I guess Poincaré first looked at this in the case when you're looking for a continuous change of coordinates. I'd like to talk more about the case when you're looking for a differentiable, or smooth change of coordinates. So, in this case, it's probably everyone or many of you know, this depends very much on the arithmetic properties of this irrational number alpha, A, sorry. So that is, so apologies for everyone who already knows about this, but let me just recount this. So for this question, we can distinguish two kinds of irrational number, the Diophantine and the Liouvillean. And these are roughly defined as follows. So supposing you have your number A, it's irrational, and you consider a sequence of rational approximations to this, so converging to this, then clearly this fractions Pn over Qn, they're both blowing up. And then you could ask how quickly do the fractions converge to the limit compared to how quickly, in particular, the denominator blows up. And if it blows up, if it converges very fast, then it's Liouvillean, otherwise it's Diophantine. So a little bit more precisely is that if it converges faster than 1 over some polynomial expression in the denominator, then it's a Diophantine, and otherwise Liouvillean. So for example, if it goes like 1 over an exponential, for example, then it's Liouvillean. So I could just visualize these irrational numbers as sort of ordered in some sense as to how fast they can be approximated by rationals. So on the left we have the slowest, to the end where we have the fastest on the right. The point in the middle in between doesn't exist, and neither does the point where the arrow is, but the one on the left sort of does, is the golden ratio. And I just looked around on the internet just to find out where pi is, and I popped it there. Apparently you can put a polynomial of order 7 or 8 there, apparently, so it will work for pi. But anyway. E I couldn't find, but so then here's a remarkable theorem is so first Hermann, if I understand rightly, proved a version similar to this first. So so for smooth diffeomorphisms, turns out that this, if you know that your number is Diophantine, which forms a set of full measures, and the other set is measure 0, of course, but is actually dense. So if your number is Diophantine, then automatically it will be smoothly conjugate to a rotation. So just from this arithmetic property of the rotation number, you know this. And I believe Hermann proved that this is true for some set of full measure, or something like this, instead of actually Diophantine numbers. And then Jokoth proved this actually the Diophantine numbers, and even moreover he showed that this is actually sharp. So for the Liouville numbers, this is always not the case, and you got the Fields mill for this. And then just quickly, so before this there was Arnold in the early 60s, I guess one of the first results with small denominators, small divisors, where he showed in the analytic case a similar statement if you assume that you're actually already close to a rotation. So, and then, of course, the first result by Poincaré for the homeomorphism case. In this case, it doesn't matter about the arithmetic properties. So it's one of the first results you encounter in, of course, in dynamical systems. Of course, you just have to have a dense periodic point, a dense point. So back to the two-dimensional question. So you have a pseudo-rotation, and Hermann himself actually asked the following question, which is more or less, does a similar statement that holds for circle diffeomorphisms actually hold for pseudo-rotations? So supposing you have a pseudo-rotation with rotation number A, that's an irrational number, then is T conjugate to a rotation whenever A is Diophantine? I mean, even if you could get a C0 conjugacy, of course, this would be really amazing. So he actually showed that that there are always invariant circles near the boundary, and I don't know the exact history, but I believe he claimed to be able to prove something like this when the pseudo-rotation is already close to a rigid rotation, or something like this. But in any case, this was proven on the next slide. I'll say this. This was proven later by Fayed and Krikorian. I just jumped ahead of myself. So then, in particular, of course, if this question were true, you'd have to have a filling of the whole space by invariant circles. So you've got this thing on the left where every orbit has the same average rotation number, and it's error-preserving, and other than that, you know very little. And you'd like to show that under the Diophantine condition on this rotation number, that you can fill up the whole space by invariant circles. That would at least be a start towards being conjugate to a rotation. So if this was anything like this is true, it would certainly be sharp. Of course, partly because it's not true for Liouville numbers just on the boundary, but also because there's a following result from the 70s, which is Anosov and Katok showed that for a dense set of Liouville numbers, they show that there exists pseudo-rotations with this rotation number, which actually are ergodic. So they typically have dense orbits and so on. So there's no way they're conjugate to rotations, of course. And then this was actually strengthened all the way to all Liouville numbers, that statement, by Fayed and Seprakina in 2004. So also really interesting results there. And then on the next slide, so also a really remarkable theorem that says that the answer to Hammann's question is yes, if you already assume that your system is sufficiently close to a rotation. That's in a differentiable sense, but with finite differentiability. And you can still conclude C infinity conjugacy to rotation. Yeah, so really very, very interesting. The global question then is not known. I asked around and people say, it's perfectly reasonable. There are counterexamples. One could imagine that there are invariant circles that as you go away from the boundary, they become sort of fractal-like, and if you're not close somehow to something integrable. So just to summarize these facts briefly is that for pseudo-rotations then, if the rotation number seems to be an important factor in the dynamics, and on the right we see if it's very Liouvillean, or if it's Liouvillean, then it could be ergodic. And Hamann asked, well, there's no counterexample, and there's a lot of evidence in certain cases to suggest that maybe if you're Diophantine, then maybe you're linearizable. So then I'd now like to talk about sort of a result that is a million miles away from any of these results I stated about. But it's a non-perturbative statement, and it's a statement about pseudo-rotations. It is as follows, that uses techniques from symplectic geometry. And this is the following, which says that any pseudo-rotation is always a C0 limit of diffeomorphisms that are conjugate to rotations. And that doesn't tell you anything about the limit. I mean, you can make other conclusions about the limit, but certainly doesn't say anything about the limit, of course, being conjugate to rotation, even if this C0 became C infinity. That wouldn't imply that. And recently, so this has no assumption, the rotation, which already indicates that this alone cannot, tell you anything about linearizing the limit. A version of this was also proven recently by Patrice Lacalves, also using techniques that have proven many rigidity results in symplectic geometry, that is, generating functions. His applies to non-smooth pseudo-rotations, but requires an extra boundary condition. So let me illustrate now. So again, what this is saying, you have your pseudo-rotation, and it says there's a sequence of maps for which you have the disk is filled by invariant circles that that are converging somehow to your limiting map, and if the limiting map happens to be ergodic, of course, that means the circles are getting sort of wilder and wilder in the limit. So motivated by this question, a natural question to ask is the following, is if you always have this, can you somehow control the invariant circles that exist for the approximating maps and preserve them in the limit? So under, for example, a Diophantine condition or a Diophantine condition plus the condition that your limiting system is close to a rotation or something like this. I mean, so that's a natural question to ask. And of course, the first thing you'd have to do is understand you've got to go well beyond the C0 level here. So the first thing to ask would be, well, you're going to have something like Lipschitz estimates on your circles, of the approximation maps. And so we want to understand what's going on at an infinitesimal level of the approximation maps. So that's what I've been thinking about on and off the last year and a or so. So far, well, I found this really very hard to make any progress on at all. So I'll say a little bit more about the construction of these, but the approximation maps are constructed using pseudo-holomorphic curves, and everything is set in a C infinity setting. You've got a PDE giving you these invariant circles, and this is the elliptic, of course, it's the Cauchy-Riemann equations. So you've got a lot of things going for you as far as sort of bootstrapping is concerned and getting actual smoothness. So it's not like the whole framework is set up in a topological setting. Nevertheless, it seems like you can't just press the elliptic button and get C infinity, like you can sometimes. So far I have the following result, which is also a million miles from what we would like to get, but let me say what this is. So we have a pseudo-rotation, and I'm going to have to make a boundary assumption. I'll explain, if I have time, that something like this is more or less necessary. And the assumption is that it's an actual rotation on the boundary, and actually that the derivative is such that you're preserving the normal direction to the boundary. So in any case, this is not a big assumption. The next assumption, however, would be, of course, is horrible and I would really like to remove. And this is, we want to assume that the rotation number of the pseudo-rotation is sufficiently Liouvillean. So that means on that line I drew from left to right, it means very far to the right. So under this assumption, we can prove that actually the differentials are uniformly bounded, at least in the C0 topology. So in particular, you get Holder convergence for any Holder exponent. Now, so two things one would like to do here. One is get rid of the Liouville condition, or at least push it into the Diophantine case to some extent. And secondly, what about the higher derivatives and so on? So this is all work in progress, so I have no idea. It may well be that for the higher derivatives you encounter more or less the same PDE as you do in the first. More or less, no, you do. It's slightly different, but there's an extra term, but it's lower order, so we have to see. And however, I'm guessing you have to go all the way up to convergence of the derivative, not just bounds on the derivative before you can start going to the second derivative. So for that, well, there is a statement, I maybe say in a moment. I should say also that even if one was able to get like C infinity convergence, and even for the Diophantine nodes, this in itself, again, would not imply anything about the limit having invariant circles. Right? Nevertheless, I think trying to do this is a very good warm-up for trying to estimate, get bounds on the actual circles. After all, that's a derivative in one direction, and here you're just trying to estimate the norm in general. I may be saying the proof where you can see what you would try and, at some point, instead of trying to estimate one thing, you would try and estimate something a little differently if you were trying to actually control the circles instead of the derivatives. So maybe I say this, and this may be nonsense, but I'll just throw this out there. At the moment, one seems to have the following statement also, which really needs to be checked, which is that you also have the following property maybe. So instead of just Holder convergence, if you take a point on the disk, you maybe get the convergence of the derivative if and only if, so I'm writing this very imprecisely, but if you make sense of the Conley-Zain a mean Conley-Zain index of an orbit that is not periodic, sort of in the obvious way, if this Conley-Zain index at that point exists, and if it's equal to this irrational number that's sort of driving everything, the rotation number, then that implies convergence actually of the derivative, and actually if and only if. So for this, but I think the if and only if here would only anyway hold if you were sufficiently Liouvillean anyway. So I don't know how interesting this is. Yes? Gamma is supposed to be the orbit here starting at a point Z. Yes, I haven't explained what this means at all. That makes it look like an orbit. Of course, at the moment, this is a discrete system. Ultimately, I'm looking at this as a suspension of this, and then it's a bit easier to talk about the Conley-Zane index, maybe. But, yeah, so basically, the mean Conley-Zane index of the point starting with initial condition z, if you can make sense of that. So Alberto told me on the airplane that he thinks that the ergodic theorem allows you to say that this should exist almost everywhere, and maybe even equals the rotation number almost everywhere. Just so, yeah, I have to look at that. Yeah. So, great, right. So I'll now stop on my slides and just say a little bit about the proof of the gradient, the derivative bounds, and then come back to talk about some other, depending on how much time I have, on another application of these approximation maps. So, sorry? Yes? Oh, I see. I can use this as well. Ah, okay. So, you don't need extra light here now. So let me just first very quickly explain roughly how these approximation maps are constructed. So you start off with so we have a map. Let me draw big. So we have this disk map. There's a pseudo-rotation with rotation number A, irrational. And we view this as the time one map of a Hamiltonian, and using the Hamiltonian, make a suspension flow. So I have a flow on here, and if I start at a point z, I flow along, and I come out at the point 1, comma t of z, of course, and I'm assuming that t has a fixed point at the origin, and we can of course arrange that the suspension is such that this fixed point is actually a periodic point, periodic orbit that just cuts through the center of every disk. And then every other trajectory is not periodic at all. And then, so it turns out you can now, so for any integer, so I guess in the background of all of this, there's a Hamiltonian, or one periodic smooth Hamiltonian on the disk. So for all n, there exists a filling of this mapping torus. Let me call it M then, by embedded solutions of so by embedded surfaces that look like this. So I have the periodic orbit running through the center, and the surface is diffeomorphic to an annulus, a half-open annulus, and it's it runs from the boundary to the periodic orbit, and it goes around, say, on the boundary, say, to here, and then, so we've got some piece of surface here. So, of course, I should, for the flow, I should identify this disk with this one by the identity map. It's not like I'm having a horizontal flow, right? And then it continues, this edge is now, say, here, and then it continues going around, say, to some point here. So it's still connecting to the periodic orbit, and then here comes to here, and then it continues on, and then here comes back, and so on, and eventually after a certain number of times, basically after going this number n times from here to here, it closes up. So each surface is, closes up after time, if you like, time n. And then each surface, so then there's actually a whole filling of here that forms a smooth foliation on the complement of this periodic orbit. And each of these is the image So each surface is the image of a solution U from a half-infinite cylinder with sort of the circle direction being length n. So half the line across a circle of circumference n, radius n, whatever. And this maps into M that takes the form S. T goes to something. So this is now a circle across the disk. And so it goes around in this direction at unit speed. So I just put a T here. And then here, there's some other map of some other function of st that's now a map into the disk, and this satisfies the equation, the Floer equation, with actually just the constant I here. So this is these are all functions of s and t, and then here I'll put say, gradient of h, t z equals 0 for all s and t here, and then of course a boundary condition. Is that z of 0 on the boundary, this is now belongs to, so z of 0t belongs to the boundary of the disk. And in fact, there's another integer going on in the background here, of course, because n only describes how many times the leaf goes around this direction, but of course the leaf is also twisting, so how many times does it go around? So you could actually say at the very beginning, for all k, now could be negative, of course, you could arrange that this is filled by solutions like this, where this map z, 0 dot, now has degree k. So this is a map from R mod n z into the boundary of the disk, has degree k. Anyway, so now if you're given this, you define a new map on the disk, and this is where the Tn comes from. That just by as follows. So so how is Tn defined? So let's write Tn of a point z on the disk is equal to, so here is a point z, or 0z. It's here. And then you just follow the unique leaf that's passing through this point. Now, of course, there's many ways to follow it, but there's a sort of a natural way to follow it. And if you follow this in the natural way, you hit some other point here, and this will be the definition of the map. So this point is some point 1, comma z prime. And so I'll define Tn of z to be z prime. So this gives you a map of the disk, and the regularity of this map is the same as the regularity of the foliation. So. And then, the first theorem was that each Tn is conjugate to a rotation and converges, there's a subsequence converging to the actual pseudo-rotation. So each Tn is conjugate to a rotation, and there exists a subsequence T in, say, J, converging to T in just the C0 topology. Okay, so then the question is, how about the derivatives of these maps here? H, yes. So the way to, so basically what's happening is that the leaves are getting closer and closer to the flow, and therefore these maps are approximating the limiting map. the rate at which they converge the flow depends on the rotation number in the background A. So when it's Liouvillean, it goes very fast. So for the derivative, there's also a nice geometric interpretation for the derivative. So let me just keep this picture up a bit. Yeah, so of course for this to work, actually I should have said more. I mean, you have to make sure the leaves winding around on the boundary, you have to choose the right integers, k and n and so on. But so what about the differential of, say, the nth approximation map at a point z in the direction of some vector v? So let's say v is unit length, and then you'd like to get some bound on this. So where z belongs to d and v equals 1, v is technically in the tangent space of z, so that's in R2. So here is v, it's some vector here, and we're looking for some vector here that will be the image of this. And unsurprisingly, this is given by looking at the linearized PDE. So you linearize this equation about this particular leaf, and then this is now so if we linearize, we get, so the linearized equation is then you look for a solution W satisfying ds W. Of course, the first two terms are just linear, and then you've got something coming from the Hessian here. S, let's write S of st, W of st equals 0. So everything here really depends on n. So looking for some solution of this linearized equation with some boundary conditions, I don't want to say, but plus the condition, the pointwise condition, that this W at somehow at this point coincides with this vector. So W equals V at the point P. It's a horrible way to write it, I'm sorry. And then this is uniquely determined because this is actually a Fredholm operator, has index 2. So for every point, there's always exactly one solution, Wn, with this given condition. And then you just look at this Wn and see what does it spit out over here. So Wn is now a vector field sitting on this leaf, and it spits out some point over here. And that's what your differential is. So somehow the problem is you have a sequence of solutions to this linear equation, and you know that the size of this solution at this point is length 1, and you want to get some bound on the length of this, on the size of the solution here. So of course pointwise conditions for a PDA, I mean, an elliptic PDA don't make a lot of sense. It's kind of, but it's linear, of course. So let me just try and give a rough idea of where the Liouville condition comes in, and so on. So what's good for us? So good is following. We have, of course, ellipticity, and we also have linearity. Bad are that the domain is blowing up now, because the domain Wn will have basically the same domain. So bad is that the domains are already non-compact, and they're getting even worse. Domains blowing up. And the other problem is, well, of course, always happens when it's linear, is that you're mapping into a vector space, and this is also not compact. So the target, of course, is compact. And this, of course, because it's linear, you could normalize, but then it changes the PDE it satisfies. So what happens roughly is that this term here in the linear equation, so this is becoming, the derivative of this in the s direction is going to 0 uniformly faster and faster depending on how Liouvillean this rotation number is here. And that's what helps you, because if this was in an integrable situation, this would be independent of s. And so in some sort of strange sense, the closer you are to being Liouvillean, or the further you are in that direction, sort of in some sense, the closer you are for this PDE in some sense to being like the integrable case. But I mean, of course, it's not a perturbation of the integrable case at all. And that's what plays a role. Maybe I say just a fraction more, which is that, so again, if this was the integrable case, you would end up with your solution. You could just do like a Fourier expansion. You'd end up with Wn of st taking the form Wn of 0t times by some exponential, say mu ns, where mu n is some negative number that would actually be, I jumped ahead of myself here. So we could, of course, this PD is an evolution equation, so we could rewrite this as ds Wn s is equal to some family of operators times Wn of s. So this is a family of operators on a sequence of Hilbert spaces. Hn is L2 of on the loops of size n, and these are all self-adjoint and have compact resolvent, so we've got a lot of nice things going for it. And in the integrable case, of course, this would be independent of s, and you can solve this explicitly. Otherwise, you would end up, and in fact you would end up with this, and mu n would now be some eigenvalue of this constant operator if it didn't depend on s. But instead we don't have that, so instead one has the following picture. So here's s going to infinity. I've got a path of operators from 0 to infinity. And for each s, you could look at the spectrum of this. This is going to be discrete. If I take some number s at random, I'm going to have some spectrum here. And we know what they are here by the boundary condition. That's one reason we need the boundary condition. And we know what they are here just because it's a periodic orbit, and things are very nice there. But in the middle here, we know very little except general properties like they're discrete and so on and so on. And this all depends on n, and as n goes to infinity, these are getting closer, like 1 over n. If you knew the same about in the middle, that would be fantastic. Of course, we don't. And what would happen, of course, in the integrable case, if you joined these up, these continuous paths would be constant. Of course, they're not now. And we have some analog of this constant here in the integrable case now becomes a function, or a sequence of functions. And then what happens in the integrable case, this would actually equal one of these spectral paths. In general, it doesn't, and it's going to be something that starts somewhere, and we have little control over it. So in the end, the proof is basically to try and show, however, that this red guy, the mu, converges to one of the spectral paths exponentially faster than the next nearest spectral path. And that's roughly what's involved. And the Liouville condition basically ensures that locally, somehow, these are getting flatter and flatter very fast. So I still have 15 minutes. So maybe I just talk again with the slides about a different direction, which some of you will have heard me talk about before. So sorry about that. So some other reasons that the approximating maps may be of interest is, so here's 3 questions. The first one I just already talked about was this question of Hermann. Another one I really will just mention in passing is this one of Katok, which is not just for 2 dimensions, but also for 3. He asks whether, for conservative systems in low dimensions, if you also have 0 topological entropy, so all these pseudo-rotations all have 0 topological entropy, are they actually, are they limits of integrable systems? So, of course, there's a lot of vagueness here, like what do you mean by limit and so on. So in the case of Hamiltonian, if your surface is a disk or a sphere, for example, then sort of the worst case you could imagine are where you have 0 entropy but ergodicity. And those are precisely the only possibilities of the pseudo-rotations. So in some sense, those should be the worst for trying to answer his question for the disk. But on the other hand, that's exactly where this approach tells you they are a limit of integrable systems. Of course, in a very weak sense, because it's just C0. But as we'll see, maybe that gets strengthened later. Another question that I'll just say something about is this, which is, again, so 0 entropy, of course, places a restriction from above on how complicated the dynamics can be. So you could ask, okay, if we have 0 entropy, can we still have ergodicity or weak mixing or mixing and so on? And if you're in higher dimensions, that gives you more space to do this. So I don't know a general statement, but one would imagine it's easier to create this. But on surfaces, say, this is, there's still some open, well, there's one open question about this, which is precisely when the surface is genus 0. So let me just say a few words about this. So the mixing question. So the question is this. So starts off with in genus 0, so the disk, which is Anosov and Katok prove that there exist pseudo-rotations which are weak mixing. So these are 0 topological entropies conservative systems with weak mixing. So the natural question to ask is what about mixing? And this is still unknown. So we quickly recall what the definition of mixing is. It just says, if we just take Lebesgue measure as our measure, but normalize it so that on the disk it has total measure 1, then it just says if you take, I'm assuming T is invertible, so I take forward iterates. So it's just saying if you take 2 measurable sets, and you take the forward iterates of one of them, I'll give you an example of one in a moment, and then you intersect it with the other set, then the limit of the measure just converges to something that depends nothing on the sets themselves and only their measures. So it basically means it's spreading the sets out very evenly throughout the space. Weak mixing, on the other hand, demands something like this, but just for subsequences. Yeah, so let sigma be an oriented surface with a smooth volume form. It's actually many of these statements hold even for unoriented surfaces, but with just an area form. So then the question is, does there exist an area-preserving transformation on the surface that has 0 entropy and is mixing? And it turns out the answer is yes for the genus 1 and higher. I'll explain that in a moment. And it's unknown if the genus is 0. So in particular for the disk, the sphere, the annulus. So the following was explained to me very honestly by Corina Olchegrai, how this idea of Arnold gives you mixing systems on higher genus, on surfaces except of genus 1 or higher. So although I'm not a specialist in this at all, I thought it's nice visually, and it relates to the question, so let me just explain this for a moment. So the idea is this. Here we have a torus, so just genus 1. And we've got an irrational flow here on this torus. And now this is just ergodic, but certainly not mixing. So if we make a little perturbation, my picture is not such a small perturbation, but anyway, you make a perturbation in such a way that you now have this sort of eye in the middle there with a hyperbolic point in the center there that's fixed. So now what happens after we've made this little perturbation. So we take a set A and see what happens as we flow it along. So it moves up here. And then it's going to go past close to the first, here I need this. It's going to go close to this saddle point just here. And close to the saddle point, the flow is very slow compared to further away. And so the points here on the red set are going to be left behind. These ones will just keep moving faster. So then the next picture, by the time it gets to there, it's gone past one saddle point. It'll have got kind of tilted a bit. And then in a moment, it's going to, of course, go past the saddle point a second time, and then it gets stretched even more. And then it's going to, of course, this is a torus, so it's getting identified, it's going to come back around and so on. And every time it goes past these saddle points, it's going to get stretched more and more in one direction. Of course, sometimes it'll go past this saddle point from this side, and that will undo the stretching a bit. But because whenever you go past this one, you only go past once, whereas here you always go past these two twice, overall the balance is in one direction. And so the effect is that the set starts to get stretched over the entire space. And that's what creates this mixing. And this has zero entropy just because it's a flow in 2 dimensions. So yeah, much stronger even than zero entropy. So I can illustrate this even nicer by the following sort of model situation. So you have the system here is you start on the bottom and you flow up by these lines, and when you get to the graph of this function here, you then jump back down as though you're moving along the bottom by some irrational translation. So you start at some point here. By the time you get to the top, you jump to some point here, and you get to the top, jump, and so on. And this is by, you make sure that going from here to here, etc., is something that's ergodic on the bottom here. Okay. And then somehow, the fact that this thing here shoots up to infinity here is a bit like the fact that you have these hyperbolic, you have these saddle points on the torus. And the real model this would correspond to is that you should have another singularity here, but it should be not as steep as this one, because here you go past the saddle point twice, and here you go past it only once. So this point here should be identified with this one. Yeah. But then everything is more clear if you make this flat. So then if I now take a set A like before and see what happens as I flow up, eventually I hit the top, and this part of the set comes through first, and so the effect is that it gets stretched in one direction, and then it gets stretched even more, and there's no counterbalancing. So eventually it stays the same measure, but it fills up it starts to evenly fill up the space. So if I now take another set B, the blue one, then of course the intersection between the red and the blue for this high number of iterates of the red has nothing to do with the sets, it's only about the size of the measures of them. So this one can show as then mixing. So this idea was used by Kerchegin in the mid-70s to show that for higher genus surfaces, you can always have mixing error-preserving flows. So of course these are not Hamiltonian, these are just symplectic, otherwise a flow is integrable. Right? And this is used by Senai, Kanin, and Uchigrai to prove all sorts of other results. I mean, because you only have to take a perturbation of the system, of the integrable system in the first place, you can even show this behavior is sort of not generic, but generic given certain conditions. So this doesn't apply to genus zero for one reason is you can use, say, the Poincaré-Bendixson theorem, which only works, of course, on spaces like the plane and the sphere. That is an easy argument to show that you cannot have a flow has even a dense orbit. So in the genus zero case, where specifically the sphere or the disk or the annulus, so the question, say, for the disk or the sphere, so work of Franks and Handel reduces the question of whether you could have mixing with zero entropy to actually just the pseudo-rotations. That's the only possibility. So the question comes down to pseudo-rotations, and then Hermann, of course, showed that the pseudo-rotations with Diophantine rotation have invariant circles near the boundary, so no dense orbits, certainly no mixing. So it's all about Liouvillean pseudo-rotations. And we also know, on the other hand, that for Liouvillean pseudo-rotations, for some of them, you can have weak mixing even, so sort of a fine line. So using the approximation maps as well, one thing you can do is show that there's a dense subset of Liouville numbers for which no mixing occurs. This is a different set of Liouville numbers to the ones which make this argument work. This one's a much smaller set. This one is basically the ones where you put exponential in the denominator instead of polynomial. Whereas for this, you need like exponential probably. Okay. Yeah. So that's another direction. Yeah, in which this applies. And yeah, I don't know if understanding the derivatives can extend this to all Liouville numbers, or it's false. Or what? So yeah. So I think I'll stop there.